Hello, hello. So thank you for having me. It's an honor to be speaking before you here. I won't start with any Spanish since I know very, very little. How many of you see any 3D printing in this room outside of this one part, obviously? There's 3D printing in this room. I don't see any. So that's the thing with 3D printing, is that it happens behind the scenes most often. It's a silent partner. But it's a vital part of our lives now. It has everything to do with our daily lives, even though we don't necessarily perceive it. It has everything to do with the car that you drove here in, the plane that you might have flown in, the toothbrush that you used this morning to brush your teeth. That's the role it plays. Because of the versatility of 3D printing, it allows us to rethink things and processes and technologies and new devices that we've never been able to consider before. An example of this. I was faced with a torn ligament a couple of years ago. And I went to my doctor and he said, okay, well, you're going to have surgery and then you're going to have to wear one of these, a brace, a cast, for 4 months. And that's misery. That means really no showering for those 4 months, at least not easily. So I said, well, can I hack the process and can I be a participant? And he said, absolutely not. That's the worst idea he's ever heard. And so I considered that for about 5 seconds and then I went back to my studio and hacked the process because I wasn't willing to wear one of these for 4 months. So the first thing that I was able to do was to take the CT data, the CAT scan data of my wrist. I wanted to find out what was going on in there. So I 3D printed it, and this showed exactly which ligament I had torn. Well, that was interesting. It's something very eerie about holding a cutaway view of your own body. But took that and started the process with digitization. Remember Peter Diamandis' 6 Ds. So the digitization process of my body started there, went to the next step here, which is a 3D scan, using a scanner that I designed, of my outer arm. So now that I'm digital, now that we've converted all those atoms into bits, we can do a lot of interesting things. I mapped the CT data against the external data, mapped that against blood flow, bony prominences, nerve endings, and now I had a map of my own body in digital. And I could use another tool that my team at 3D Systems designed that could actually 3D sculpt on that 3D surface. So we used that device and created this cast. We called it the bikini because it covers absolutely the important bits and nothing more. But when you think about it, that's all you really want in a cast. You want to keep your wrist from moving for 4 months. That's all. The rest of it, all that fiberglass wrap, that's just because we haven't really thought of it a whole lot since the Romans started that whole process. And so what this allowed was then I just had to simply turn those bits into atoms, and that's the 3D printing process. Now I had a big pile of atoms that I could use to fix the original pile of atoms, which is me. And immediately after surgery, I cut off the cast that I didn't like, and I put this on. And one of the things I found is, okay, suddenly I could put hot and cold compresses directly on the surgical site. I could massage the scar tissue. I could get acupuncture. I could have sunlight directly on the arm. Most importantly, I could shower every day. I went scuba diving. These are things that you can't do when you're recovering post-op. So I promise this is the last you'll see me naked before a cocktail hour. So wore this for 4 months. I healed way ahead of time. My doctor then accepted, yeah, this was probably the best post-op stabilization that any human being has ever received. And this is all because of a digital workflow, going from atoms to bits back to atoms. We're able to rethink a process that really hasn't been changed significantly since the Romans. So we looked at what could this look like in the future, and we thought, how about something like this, where we print directly on the body? A little bit more fanciful until we found out that, yeah, there are actually groups working on directly this. So in the future, you might go to the doctor and have yourself fixed, directly 3D printed onto your body. Well, 3D printing was never meant to do this. 3D printing only ever had one goal in mind, which was to make car dashboard prototypes faster. 35 years ago, Chuck Hull decided that was significant to impact the economy of the US, make car dashboards faster. That was back in the early age of Industry 2.0, where you're simply doing manufacturing and assembly, old school. Well, what he added to that old mentality was the ability to create complexity at no burden to the system and to do it very rapidly. And what he didn't realize was that he ushered in an age where all these things came in for the ride. Once you can do those two things. So you take all the processes here on the left, the rolling, the cutting, the stamping, deburring, all the nightmare processes here, and you replace them with what you have on the right, atomize, print, done. And all of a sudden, when printing makes sense for a certain industry, it absolutely dominates it. To be sure, there was the hype cycle that we see a lot of. Back around this time here is when people thought that if they dropped a blender in their counter and it crashed on the floor, they could simply press a button, print it, and boom, a new blender would appear for them and would enter this fantastic age of consumerism. That never happened. What did happen, though, was that 3D printing quietly behind the scenes was entering every industry and revolutionizing it. So, back to the original grid here. When you take a couple of these, a subset of these elements, now we look at what is prototyped on a car now. It's not just the dashboard, it's the entire car, right down to the optically clear headlights. But more importantly, the migration isn't stopping there. It's going to printing the entire car itself. This is a Bugatti with really cool wheels that couldn't be made any other way. But it's not just really cool wheels on a Bugatti. Mercedes is keeping old cars alive by printing parts on a car that's been dead for years to resurrect that car. Not just them, it's the humble tractor. It's the humble washing machine. Whirlpool is trying to increasingly integrate 3D printed parts into their inventory. And in fact, there are third-party groups that are looking at having their own digital libraries of inventory. And the reason for this makes complete sense. If you're a company like Whirlpool, the one thing you don't want in your life are vast warehouses with box after box of parts that may never be used, trying to keep old products alive. Well, now what they can do, if they have more 3D printed parts, then they simply have a digital inventory. They can keep their entire inventory on a flash drive and call them up on demand. They don't want inventory, they want happy return customers, and they want profit margins. Now they get the second two without wasting time on the first one. But take the inventory aside, and you get the rapid development cycle, the other part of the other dividend that comes along with it. And it's all about shots on goal. How many parts you can create, how rapidly, so that you can do that design, fail, learn, design process. The faster you can do that, the more parts you have, and the better your design process. Well, nobody does that as aggressively, perhaps, as Formula One. They're in a constant iterative cycle. Well, the way it used to work is designer comes to work, designs a part, sends it to the machine shop downstairs. They spend weeks machining that part. They take it to the wind tunnel, get their telemetry data, go back, design. So now what happens, because of 3D printing, is first 8-hour shift designs part, second 8-hour shift prints part, third 8-hour shift wind tunnel tests part, and by the time the same designer comes to work the next day, she has all of her data from the day before sitting on her desk ready to design the next part. So you can imagine, if you are a Formula One company and you have not fully embraced 3D printing, you better just bow out gracefully. You don't have a chance against this. And that's kind of the nature of 3D printing here. Well, so unrelated to development cycles and inventory, you have part consolidation. Now, anybody who's ever had a Ducati knows what this is. This is what your weekend looks like. It's a lot of parts. Remember the 12 to 20,000 parts in an internal combustion engine? Machines don't like to have a lot of parts, they just have to have them. It's just the nature of complex machines. Well, every time you have more parts like this, you have the cost of tooling, the complexity, increased size, weight, everything about it, inherent weaknesses, things that'll leak, things that'll break. But when you're 3D printing something, instead of that, you simply print all your functionality in one complex part. And so what we're seeing more and more are parts that start looking like this. All the complexity is built into one part, and you get the savings on all fronts. Now, complexity also brings in a range of other dividends. For example, back to the really cool Bugatti wheels here. It's not just the wheels that are benefiting from 3D printing anymore. It's the tires. So 3D printing tires, they're not going to print the tire, but tires come from tools. It's a big jello mold, and you shoot hot rubber in it, and you get a tire out when you open it up, and it cools. So in this case, the tools have always been limited by the ability to create a very complex shape. Now that you can create any shape you can dream up, the treads are far more advanced, and they have a better wet road adhesion than ever before. So we're seeing a new generation of tires that can handle wet conditions coming about. In fact, let's just print the entire car. That's what Local Motors is doing. And they have a number of different cars that are looking at very small batch run production cars for very niche markets. They can turn on a dime. Unlike General Motors, who takes years to make any changes, these guys can change the next iteration. So the next generation car might look something like this, where it's massive part consolidation, highly optimized, highly organized. Now you take all these ingredients, and it's pointing to something we call Industry 4.0. And that's about cyber-physical systems. It's about integrating computers, making autonomous decisions right into the manufacturing process. And we're seeing this, in this case, with robots printing the actual parts themselves. So the robots are printing the parts on demand right there on the assembly line, integrating them into the parts as they're being built. If you need more bandwidth on your robots, you simply add more robots to the assembly line. But now it's not just that the robot is prepping the part, printing the part, and assembling the part. It does another step in the process, which is it's inspecting the part. It 3D scans each part that goes through, it compares it against the known data set. And if there are defects or problems, it makes the accept or reject decision autonomously right there, and it can pre-compensate the very next part that it makes, because it knows where the defects are and it knows the kind of compensation needed. So that's all happening autonomous. Lights out, no humans involved factory. Well, we're seeing that now also in the mass production of shoes. In this case, we're seeing 100,000 future craft shoes that are going to be made this way. Now, the shoes, to be sure, are certainly very complex. There are 20,000 struts in the sole of this shoe, so it has mechanical characteristics we've never imagined before. But athletes have been taking that one step further for quite a while, which is that the shoe is actually printed based on a 3D scan of their body, and it's specifically tailored to them. So now you need mass customized shoes printed per person. We're not there yet, but all the indication is that we'll get there. We've already done it with braces. This is Invisalign, which prints 17.8 million individual customized aligners like these per year. And it's revolutionized orthodontistry. So now you add two more ingredients there, optimization, biomimicry. Well, optimization is something that humans do really, really badly. And I can say that as a designer. We just don't do it very well. Part of it is that we've never been able to. We haven't been able to consider it because when the means of fabrication and production are as limited as current manufacturing, you can't really think in terms of these very broad sense. You can't think in terms of the idealism that you'd like to up front because you can't make it in the back end. You're limited by the means of production. Now, the very best 3D printer in the world, of course, is nature. It prints in very optimized structures using the materials the right way, just the right amount of materials. Well, suddenly now we have new tools that can make products according to demand. So we're seeing that this principle, something called Wolff's Law, the distribution of material based on necessity, that can be factored into the parts that we're creating. So for example, airlines are drinking this up because they can make parts that are much more efficient, much better strength to weight ratio and all the principles they need, so they can make planes that are much stronger, lighter, and have much better fuel savings. Formula One again, 3D printed parts, structurally optimized. So I was asked to do a demonstration of this for the Cooper Hewitt Museum in New York, and so we took the Humble skateboard. We said, okay, let's apply this process just so that people understand what this process topology optimization is. Now, by contrast, traditionally, a designer would design a skateboard, put it on the market. If it broke a lot, they would make some adjustments, introduce it back on the market. Well, now what you do is you relinquish the control of your design to the software. Instead of designing the skateboard, you design the conditions in which the skateboard will exist. So you load up the forces in it, you load up the conditions, you load up everything you can anticipate. The software designs it, and then you simply 3D print it. That's a quick proto. Here's a typical large machine, powerful lasers. It prints it, and now you'll see in the background here the 3D printed titanium parts, the carriage that holds the wheels down below. So we fully assembled it and made the first highly optimized skateboard for no real purpose. But one of the things that you find that's kind of interesting is that the farther we delve into super, super high technology, the more we start returning to nature. This looks more like you dug it up out of the ground under a tree than something that came from state-of-the-art technology. But this is what optimization looks like. Now, it's not limited to skateboards. We're seeing motorcycles get involved. And it's actually not limited to structure either. You see here, these are heat exchangers. They're radiators. And radiators you can make far, far more efficient because you can create shapes that were never makeable before. So these are going to be the heat exchangers, radiator, and cooling devices of the future. They're 3D printed. They're highly optimal. And it's not just those. This is a injector nozzle on the new 777 by Boeing. And it has allowed them 10% fuel savings. One 3D printed device, 10% fuel savings on an aircraft. So the dividends are many. Now, staying on aircrafts here, the next generation of the aircraft might look something like this. Large product, biomimically designed, structurally optimized. Now, the one challenge here is that it is larger than your 3D printer. 3D printers typically limit about that scale. So how do you print outside the box? Well, that is what a lot of groups are looking at now. This is a group where I live in Amsterdam called MX3D, and they have solved the problem, or they're addressing the problem anyway, of 3D printing outside the box by letting the printing devices, in this case robotic armatures, climb the structure that they're printing. So they can print, in theory, an infinitely large structure. They are using biomimicry, low quantity manufacturing optimization. Here's the bridge that they printed. This is going to be installed in the Netherlands, in Amsterdam. I walked across it a couple weeks ago. It's a big, beautiful piece of stainless steel. China has been doing the same thing. They printed this in 30 days. The military is doing the same thing. This is exploding right now. There's a lot to be learned. It's very nascent technology, but we're seeing more and more construction being done this way. And here you have Dubai looking at drone printing, where the drone does the printing. They're looking to, you see, print 25% of their buildings by 2030. It's very aggressive. But we're seeing that as well. The takeaway with 3D printing of architecture is that we just don't know where it's going to go. There are a lot of different methods, and people haven't really sorted it out yet. And the codes haven't even been developed enough to catch up. This is an architect in Berkeley, Ronald Real. He 3D printed each brick site-specific, so it's specific to its location on the piece of architecture. And what's kind of cool is each one is a vase, so that it's a living structure, and it purifies air and water while looking really beautiful. And this is the house that was mentioned yesterday. The goal is to print these for about $4,000 very rapidly, very low cost, very high quality. There are a lot of different groups looking at this now. Or if you want to take this farther afield, this is a concept from the Clouds Architecture group looking at how we will print on Mars. Now, Mars has the raw materials, water, and it has the need. We need a big structure. We need it to be light transmissive so that our potatoes will grow. And a couple meters of printed water, of ice, will stop the gamma rays and bring them down to a survivable level. So when you live on Mars, this might be what your home looks like into the future. So as an experiment, this is what my team at 3D Systems looked at. This, of course, is a rocket part, staying on the space theme here. It was 3D printed using, you don't want to take a guess what it was made of. Yeah, a meteorite. Meteorites often are nickel and iron, which are two of your best building materials. So we ground up the meteorite, processed it, 3D printed from it. Because if you're going to be doing manned space, life in space or manned long-term space travel, it's really nice if your raw materials are already there, because the hard part is getting them from here to there. So the only trick is that when I'm 3D printing on the ground, my raw material is in a bag over in the corner. When I'm in space, my raw material is going by at about 20,000 kilometers a second. That makes it tricky. If you can do that, you're good to go. Now, the big sweet spot, as it has and probably always will be, is medical printing. Now, this itself is a 7-day conference. You could go on forever about medical printing. They say something like 80,000 parts are printed per day for medical applications. It's the important one, and for all the obvious reasons here. High user value. Yeah, it's as high as it gets, right? Complex geometry, custom manufacture, rapid turnaround, digital workflow. To sum it up, you can look at the 4 main characteristics. the preoperative planning, perioperative guides, meaning once the cutting is started, osseointegration, meaning something that integrates with your body, and then the exoskeletal fixation, something that happens after the fact. So the first one, body-specific data visualization, this is all about if the doctor knows better what she's about to get into before the surgery starts, that knowledge will lead to a better surgery, better outcomes. So what they do is surgical planning devices. This is essentially a 3D printed roadmap of liver samples. These used to be very expensive. Now they cost about 90 bucks a pop. So it's too cheap not to do. And you can see exactly what you're going to be getting into once the surgery starts. You have a model that you can hold in your hand. Or in this case, you've got models of the patient, patient-specific models here. And you can test drive what it's going to be like to cut into them, to bolt the parts down, the 3D printed parts down, and everything else. Now, once the cutting starts, the whole goal is to be accurate and fast. And so, in this case, a spinal brace, spinal rods put in. If a doctor was going to try to print or to drill all 16 of those holes that you see going up and down the side, knowing exactly where to put the drill, how far to put it, what angle to put it, they'd never get there. Humans just are nowhere near that accurate. The best doctors alive can't do it. But instead, you 3D print a brace like this, the doctor simply puts the drill in the hole and gives it a push. Anyone can do it. And each hole is in the exact right location. You bolt the cage down, it's going to be perfect every time. So it's going to be less rate of rejection, much faster process, which is blood loss and cost issue, and you're going to get much better overall outcomes. So this is being done now. These are called pre-surgical guides or perioperative guides. Now, if anyone in the room smokes, chews tobacco, or likes to shoot things while drunk, believe it, that's a medical category right there, those three. You don't raise your hand, but do pay attention. What happens if you shoot things while drunk, very often you end up shooting your jaw off. Go figure, that's America. Tobacco products generally lead to a tumor the size of a breakfast roll in your jaw. You go to the doctor, they say, hey, your jaw is going to have to come out. We have to resect your jaw. That's never good. It's usually a death sentence, unless you really like soup and you're kind of done talking. So you're now saved. You have a solution. They open your face up, then back up. They put you to sleep. They open your, sorry, this is like right before lunch. They open up your face, they bolt down these guides, they chop off the part that you're no longer going to be using. Your jaw now looks like this. Now the doctor at the other end of the table has meanwhile opened up your leg, pulled out your secondary leg bone, your fibula, dropped that on the table with other guides that they bolted down. They chop it up into these nice bevel cuts. They put the bevel cuts in. They're already vascularized. They're going to work on the body. Your body won't reject them. They bolt the whole thing down with a 3D printed plate. And while they're at it, they throw in some 3D printed teeth. Dentistry and 3D printing is an exploding field. And now, once you've recovered, you're back to chewing tobacco, smoking, or shooting things while drunk. So take my number down. This is not readily available surgery. This is still the exotic stuff. So if this happens to you, be sure to give me a call. Or, in this case, you probably just want to send me a text. It's up to you. Osseointegration is the last of the areas. It's what you leave behind in the body to fix your parts. So the ability to 3D print something with infinite complexity means that you can print these parts that are porous lattice structures. And that's exactly what promotes bone ingrowth. So in this case, a hip cup, acetabular hip cup. Tens of thousands of these have been in people so far, and over the last 10 years. So it's been a proven success. They're bolted into the person, but then the bone grows in and through it. So pretty soon that 3D printed part simply becomes a part of the body. This has already been proven successful. The next step, that's only a stopgap. The next step is where things get exciting. The Fraunhofer Institute last week announced a process called plasma jetting, where they plan to print the scaffolds that they drop into the body. The bone will grow in and through them until the scaffold goes away, and all that's left is the bone that's replaced it. So the 3D printed part goes away when it's done. Now that's already done with this really great material called polycaprolactone. And it's a material that can be printed on a desktop printer. Nothing fancy at all there. Now this is a stent for children for the bronchia, the trachea. Collapsed trachea, they need a bronchial stent here. And traditionally, if that's metal, it requires a lot of surgery, has problems all over the place. Now what they do is they simply 3D print it out of polycaprolactone. Now it has almost a programmable rate of bioabsorption, meaning that it will hold the child's passages open, and then over the course of a couple of years, while they are being aided by that device, it will then be absorbed by the body. So when it's done, it's simply gone. So it's like the cowboy that fixes the town and then goes off into the sunset. You know, it's like a little Jim Cagney, just gone when it's done. It's done its job. This is Dr. Julie Lin Wong. She is an alum of Singularity, and she looked at all these and said, well, supply chain problems also lend themselves to 3D printing. So she came up with something called 3D for MD to address supply chain problems in the hardest place on Earth, which is the International Space Station. She worked with Made in Space, another group from Singularity, who created the first 3D printer that works in space, and this is printing daily now on the space station. And the first part they printed is one that I worked with her to design. This is a finger splint. And what you see in the background there is Earth. So what's strange about this is the digitization in the Peter Diamandis list, that we sent the file to the space station as a bunch of ones and zeros. We essentially faxed a 3D part into outer space. It's the first time a part got into space without being strapped to a big old rocket. We beamed it there, right? So she's looking at all the parts you might need for long-term manned space life. So you can 3D print your entire inventory of hospital items. Now, you take another problem here, something called amniotic band syndrome. And it leads to children having not fully formed hands. Now, here's a challenge. Each hand is going to have a totally different subset of deformations to it. And so there's no one size fits all with this. So in this case, there's an app for that. You know, that's when you know you're living in the future. There's an app for a birth defect. And the way this works is you simply go online to the Enable Foundation. You describe through a series of checklists what the nature of that problem is. It decides to create then automatically a hand that will fit that specific patient. And it will download a print-ready part. The part you can print on a common consumer household printer, this one I designed for about $1,000. And these guys now, whoever wants, can download that part, print it, and send it to the kid. The cost for that is about free, because it's a trivial amount of material cost. So we're seeing more and more, there are kids printing for other kids. The weird thing is what they don't realize is they become then a manufacturing site. So they are a distributed, philanthropic, peer-to-peer manufacturing site. Now those words have never existed before. You can't really put those together because they've never existed. But that's one of the things that 3D printing allows. And that is also the dematerialization that Peter's D's talk about. They've dematerialized it. They've also demonetized it. It's a free process. And because a lot of kids have these 3D printers, they've democratized the 3D printing process, the ability to create a part for another kid. Here's the part that comes out of it. It's a fairly simple hand. It just has basic grasping motion, but it allows the kid to eat, to open doors, to dress themselves, to hold things, to carry things. But there's another democratization that went on here, which is that anybody who's got an interesting idea to improve on this can simply design their own hand, as this guy, Evan Kuster, one of the guys on my team. He designed this hand, he put it onto the Enable site, people like it, and so now people are downloading his hand. So again, democratization of the design process enabled by an all-digital workflow. And these hands are simple and crude for now, but 3D printing is getting, the more advanced 3D printing is finding its way to the desktop. So these stronger, durable, more accurate materials are finding their way downstream, becoming lower cost. And we are envisioning a day not far off where a hand that's loaded with complex sensors, actuators, some processing power, that will be 3D printable for almost no cost. And so all of a sudden, somebody who needs a very complex hand like this has access to one like nowhere before in history. A complex bionic hand for almost no cost. That's what we're seeing. So a process that was really only ever meant to make car dashboards faster opened up the law of unintended consequences when people started hacking it, using it for things it was never intended for, and creating parts, creating all kinds of designs based on these dividends that came about. And that is the nature of innovation. It's the nature of the Ds of Peter Diamandis. It's the nature of rethinking the entire thought process. Thank you for your time.